start off with the COVID-19 presentations. This set of presentations will include student speakers from 4 different tracks who have worked on solving challenges related to COVID-19. We're going to be moving on to robotics and its intersection with COVID-19. The challenge for the robotics and engineering track was to design a ventilator that can be produced with more versatile and everyday supplies and become more portable and smaller in size. So without further ado, let the teams take it away.
Hi, my name is Aryan, and this is our approach to the COVID-19 ventilator project by Avik, Alex, and Nandana.
Because of COVID-19, ventilators are in short supply. The main issues with current ventilators is that they're, 1, hard to use, which means that nurses have to waste precious time learning how to use an ICU. The second issue is that they're clunky, which means that portability is out of the question, which means that home visits won't work. The third problem is that it's really expensive, which means that most hospitals can't afford too many of these. And the fourth issue is it's extremely hard to manufacture, and that's getting worse due to the fact that COVID-19 is removing jobs.
So we did some background research, and we learned that there are 2 types of ventilators, non-invasive and invasive ventilators. We learned that non-invasive ventilators are the cheapest and the most cost-efficient, and non-invasive ventilators involve the use of face mask or a helmet, while invasive ventilators involve like a surgery where you have to insert a tube into a trachea, and we learned that non-invasive ventilators are more effective in treating patients with COVID-19, according to the FDA.
Our ventilator system will consist of 1 giant screen and 4 ventilator units connected to it. The ventilator units are connected to the giant screen through Bluetooth, so it saves more space and is much more portable. The screen will display the patient's oxygen levels and other crucial information. Hence, the doctor can remotely check our multiple patients from a single location, allowing them to be safe from COVID-19. Each patient would have their own ventilator unit, which will consist of oxygen tubes, motorized pushers with rubber pump, and a mass airflow sensor. Additionally, the ventilation units are made to be compact, making it portable, and this also helps to improve the mobility of the patients. Plus, these ventilators are also able to predetermine the pressure support needed for the patients due to the sensors and platforms we have incorporated in it.
Okay, so the first image to your very left, we decided to go with only the necessities as we wanted to make it really easy for the people to manufacture, and also we wanted to make it really compact and portable. So as you can see, there's a rubber pump, and then there's 2 linear actuators which are connected to a wall, and that will push the rubber pump depending on what the platform informs the linear actuators to do. So the platform is connected to a mass airflow sensor, which is on the NIV helmet on the tube. So basically, the mass airflow sensor will determine like the pressure support needed for the patient as it's connected to the tube, and that the mass airflow sensor will send that data to the platform, where then it will inform the linear actuators to like press the rubber pump at certain speeds, providing the pressure support needed for the patient. And then also to your very right, you'll see the ventilation system, the whole device. So as you can see, the NIV helmets are connected to the ventilator units, and then those little blue like rays are the Bluetooth basically, and they're connected to the giant display, which the doctor can check remotely.
This CAD model shows the ventilator system being in use at a hospital. As you can see, each patient has 1 ventilator unit with the motorized pushers, rubber pumps, and tubes. The display screen is in a separate room, which allows the doctor to monitor the patient's oxygen levels. Therefore, this ventilator system is portable and efficient.
I also have something to add. Those helmets are also made out of antimicrobial materials, meaning like it prevents biofilms, which are groups of bacteria from forming. So that gives it the ability to actually use it like once or twice. So this is like the format of like what it should look like when you connect the ventilation systems to the display. So the max amount of ventilation systems you can connect to the display are 4, and each of these boxes will provide information about the patient, such as the number, as well as like the name and like age as well. And then there's also the oxygen level count. And then there's also an alert. So basically, the platform can detect if the patient's oxygen levels are like lower than a certain number.
Okay, thank you very much for that presentation. The the next group can continue.
So hello everybody, my name is Sharya Sharma, and my partner Daniel Martinez will be presenting our slide presentation that is called a ventilator crisis. So our problem. With the increase of COVID-19 cases around the world, the high demand for ventilators in hospitals has caused a sudden shortage of them. To solve this problem, our team here at STEMATIX Labs has designed a ventilator that is portable, inexpensive, and is made with everyday materials. This makes our ventilator easily accessible by patients who don't have access to normal ones.
As you can see here, the ventilator pushes warm, moist air to the patient. Exhaled air flows away from the patient through tubes.
So this is a description of our ventilator that we created. So the ventilator functions with the motor that turns a disc with a little nib that is offset from the center. Next, there's a belt that goes around the nib and around the bottle. So when the nib goes down, the belt compresses the bottle, which makes the bottle squeeze air. When the air goes out of the bottle, it goes through a valve. The valve is essentially a gate that is airtight. And when the air goes out, it opens. And when the air gets air in it, it doesn't take infected air in. After the air goes past the valve, it goes into the mask, which simulates a patient's mouth. The infected air then gets sucked out through a pipe by a fan at the end of the tube, the outtake tube.
So here you can see a CAD model of our ventilator. You can see the motor, which spins around a disc with the nib offset from the center, and around that a disc is a belt that pushes down on the empty water jug, which you can see above. The valve is that orange cap thing that you can see on the bottle, and through that there's the air goes through the valve and then through tubes into the patient's mouth through a mask, and the exhaled air goes away from the mask and it gets pushed out by a fan at the end. This is our background research. And this is our bibliography.
Thank you for listening, and we added a little quote. So when something's important enough, you do it, even if the odds are not in your favor.
Okay, thank you very much. That was a nice presentation, and thanks for adding that little quote at the end.